Hello. So last time we looked at the fixed law solution, or in the video on this one, we did this, and we compared this to a histogram we made of our random walkers, our 1D random walkers, where we get results like this. Here, where here's the analytical solution from the fixed law solution, and then we actually have the histogram of the random walker. So it's like what I did is I took where the random walkers were, and I binned them. I divvied up the length that they could have possibly traveled into little bins, and I counted how many are in bins, and I get this graph here. So that's what we're going to show how to do that, because making little histograms like this is useful in a lot of cases. Like there's the homework now, we're doing concentration, we're radially profiled. We might want to do something similar there. So this is all done in my 1D random walker code, which was, we went over the solution earlier. But I've added a little to this. I've added this delta x here, which is my bin length, and then okay, I have to give that histogram a length. I can give it here by this, which is similar to the fixed law, 2 times how much time I have divided by the delta x. So I have to define a length of my space. So it's the length, the physical length divided by the resolution, the bin size I want, and then I define my bin size here, essentially. And this code is the random walk we've seen before, right? I have the switch case, this case 1, meaning coin flip, or it could be 2, meaning the probability distribution. I assign the various variants. And then when I get done, after how many time steps, I go ahead and print, do the histogram, which is this function here. That's what we're going to look at. So it is a void. It takes in an array of doubles. So what it first does is just creates an array, h, whatever you want, of length, l, length, whatever that can be. I put it in as length here. So you might have, instead of, in this, you might have c length in, say, your concentration one, but it doesn't really matter. And then I have this bin. So what bin is in my film? So the first thing is just this for loop here. Just sets all the bins equal to 0. So there's no counts. And then I read in whatever data I'm going to put to bins. In this case, it's my position of my random walkers. I just give it this variable here so I can look at it whenever I want. So sometimes when you do allocated memory to make arrays and you put a breakpoint, this won't print out what the value is when it hits the breakpoint. So I just give it another variable for a placeholder and then read that variable in. Just a little trick. So what bin is that going? That's the next part. Because we don't want to do some double for loops or embedded for loops. So say, is this between this and this? We want to just cycle through our data set once and fill the bins as we go. So first of all, since my random walkers can go from their possible range of values goes from negative, say if it's time 100, negative 100 to 100, because like the coin flip, there could be that one lucky one that always goes the same one all those 100 time steps, which is what I'm going to recenter that. So I'm just to add a constant to it, Tn. That way all my values of my random walker, of their positions, start at 0 and go to 2 times the possible length, which is the end time. And then I divide that by my delta x, my resolution, my bin resolution. And I'm casting this into an integer. So that would give me an integer. Then I say, okay, this is the bin it goes in. I just put that in there as my index. It's an integer, so I can do that. And I just say, okay, add 1 to that. So let's look at that. Oh, didn't hit it. What's going on here? Oh, right there. There we go. So we have negative 18. So you add 100 to negative 18, you get a bin of 82. Delta x is 1. If it was delta x was smaller than 1.1, then it'd be 108, right? Uh, good, and then that increases that bin, and then so on and so forth. So let's say we're doing concentration with R. We're gonna radially go out and say, okay, we have these shells of radius delta R far out, and we do the same thing. We go to our position in 3 dimensions. So what's the radius out? What's our resolution? What's our delta R? And we don't have to do this. We wouldn't have to do an offsetter there because it starts at 0 and goes to R. It's the possible instead of going from negative uh, final time to positive final time is the range. So that makes it easier. And then this the same trick here. This is one of those instances where we're using integer math helps us because by making this casting this an integer, it cuts off any decimal places. So say for case 2 here, and then let's go ahead and make my delta x, and now let's run it. Builds, runs. Because this won't be as easy as the coin flip one. So -8, what bin is that? 119. So you add 100 to that. You end up with a little thing less than, you end up, yeah, 119. So yeah, that makes sense. Yeah, so add 1, yep. And there you go.